This week we're going to look at the Fundamental Theorem of Calculus, Part 1. So we're going to shorten this to FTOC Part 1, because that's a lot of words to say every time. And the statement is, if f of x is continuous on a to b, closed interval, and differentiable on the open interval a to b, then the integral from a to b of f of x dx equals big F of b minus big F of a. And big F of x or big F of b, those are the antiderivatives of f of x. So using this, we can find the net area between a function and the x-axis. So this does connect to Riemann sums. Riemann sums were estimates, and we'll talk about this a little more in the live sessions, and we'll connect those two together. Okay, so in this example, find the area between the curve and the x-axis where f of x is x cubed from -2 to 1. So we're going to set up an integral, and let's just do that first because that's the point of this. So we're going to have the integral of x cubed dx from -2 to 1. So you're always going to put your lower bound in the lower and the upper bound in the upper. So let's look at the graph though first, and we can talk about what this means graphically. So we have the function x cubed, and we're evaluating from -2 to 1. So what this is going to do is it's going to calculate these areas. And this area. So we're going to have a positive area. So we'll talk about that. This is positive area. And this is when you're above the x-axis. And we're talking about that piece. And this would represent negative area below at the x-axis. So sometimes you're going to get a negative area, and that just means that the area is below the axis. And depending on the context of the problem, you might make that positive. Just depends on how the question's asked. So that is what we're going to calculate. You can see in this one, we're probably going to get a negative area because we have more negative area than positive area. So that's what the integral graphically would represent. And then calculating this is just what we did before. We're going to find the antiderivative of x cubed, which is x to the 4th divided by 4. And then the notation is new here. We're going to evaluate from -2 to 1. And what we do with that is this. We just evaluate. So I'm going to write it down here. This would be the function 1 to the 4th divided by 4, subtracting -2 to the 4th divided by 4. So I'm just plugging in 1 and -2 for x and calculating. So this is not like doing Riemann sums, which are clunky, but they do define the definite integral. This is much easier. So this would just be 1/4 plus or minus 16/4. So 1/4 minus 4, which is going to give you -3.75. So that would be the net area between x cubed and the x-axis. All right, so we have a trig function. So we've done most of these types of problems already when we were doing indefinite integrals. So hopefully this is easier. We're just evaluating now. So this one will be sine, because we take the derivative of sine and we get cosine. And we're going to evaluate that from 0 to pi over 2. Notice I don't have the c, and I don't need the c because this is a definite integral. We have boundaries, so we don't need to have the c when we have definite integrals. And then we just evaluate. So this would be sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, sine of 0 is 0, so this is equal to 1. Okay, so let's look at this one. 1 over x squared. 1 over x squared evaluated from -1 to 3. So you can't always just jump into evaluating because the function does have to be continuous on the interval. So let's look at 1 over x squared on a graph. Okay, so this is 1 over x squared. And you can see that at 0, the function is undefined. So there's a vertical asymptote. So for that example, this is not possible to evaluate the integral using those boundaries. So we would say this doesn't exist because it is not, it's not continuous on that interval. Now what we could do is change the interval. So as long as we're not evaluating across 0, we can do this one. So we would have the antiderivative of this. So if I rewrite this, it's 1 to 2 of x to the -2 dx. And then calculate the antiderivative, which would be -x to the -1 evaluated from 1 to 2. And we're going to evaluate, so this would be -1 over 2 minus -1 over 1. So this would equal 1/2. And so these are just some simple examples to get you started, and we'll work some more out in the live sessions, but that is ultimately what we do. It's just find the antiderivative and evaluate the antiderivative.